So this is chapter 24, part 3 video, last video of the semester. So chapter 24, part 1 was about alkanes and naming. Part 2 was isomers, and then alkenes, alkynes and their naming, and then being introduced to aromatic hydrocarbons. So this last part, so again, just a quick reminder, all the content in chapter 24 in our textbook, we're not learning everything that's in chapter 24, because that would almost be Organic Chemistry 1, the course. So we're not doing that. These are the things we're learning. So the naming for alkanes, alkenes, alkynes, knowing what isomers are and drawing isomers, recognizing aromatic hydrocarbons, and then recognizing some other categories of organic compounds. So we are not learning to name these categories. This last video is about these categories. You're going to learn to recognize functional groups. So when we were naming, we learned how to name alkenes, and alkynes. Alkanes aren't really considered a functional group because they're like the simplest organic compounds, but they really are. Alkenes and alkynes are also considered functional groups. So what that means is they're just different categories. They're just different families of organic molecules. So we're going to learn to recognize some of the most common families. So the way to it's being able to, if you see a molecule, circle the part of the molecule and give it a name. And I'll do an example of that at the end. So it would be something like if I drew a molecule and it had a double bond between two carbons, that you would circle that double bond, and next to that, write alkene. That's what I'm talking about. Sorry, my Shih Tzu wanted to come in. So these are just the different categories of functional groups. So in the chapter 24 folder on Canvas, I think it's our third handout that says organic functional groups. That has the table that I'm getting ready to show you right here. It's this as a file of all the different functional groups. Now you can see at the top, alkene and alkyne are on there. I don't have them listed in this PowerPoint slide because we've talked about them already. Haloalkane, which is right here, I'm going to cross out. It is a category. I'm just not holding you to that. All the rest of them are the things that you need to be able to recognize. So I'm putting a check mark next to alkene and alkyne because hopefully we already know those. And we're going to talk through these other ones. Now, I'm not going to go through the order of these in the way that they're listed because when I had to learn these the first time, I kind of grouped them in a way that made sense to me and it helped me remember them. So I'm going to go through them in the order in which I grouped these molecules. If at the end of the day you don't like my grouping, I don't care how you learn them. I want you to recognize them. Now, in a normal semester, I would suggest flashcards where on one side you will put the functional group, like you would draw that picture. On the other side, you would put the compound type or the family type. And that's how you would learn to recognize them, by like looking at the functional group and then you coming up with the compound type name. And I still would suggest that. It's going to be a little bit different with the way that we're testing this semester. In terms of, you're going to have resources in front of you. But again, you're going to be recognizing this. We only care about these first two columns. The third column where it says suffix or prefix, if we were learning to name them, that's like, the first two, alkene and its suffix is -ine and alkyne and its suffix is -ine, like we know those. But the other ones, these are what they would be. We're not learning that, okay? You will learn that in Organic Chemistry 1 and 2 because this naming, it's a lot, so some of it carries over between the other semester. So if you think it would be helpful, you can definitely hold on to this sheet for when you take organic chemistry, whether you take it here or somewhere else. It doesn't matter. All of these things, this is organic chemistry is organic chemistry. The only differences between where you take it are the number of your best friends in class with you, either 499 or 19, or in your professor. So like everyone, I don't care where you're taking it, you're going to learn how to name all these in organic chemistry. So if you think this would be helpful, keep it. You'll definitely get this information when you take organic. So we're just going to go through the functional groups. I give you a couple of fun facts about them. And then, then at the end, I'm going to write them all out in a different table other than this one, in the way that I've grouped them. So first, functional group to talk about are alcohols. So alcohols are organic compounds that have an OH attached to them. Now, you look at that and you're like, oh wait, you talked about OHs a bunch this semester. Those were on bases, like the 8 strong bases had OH. That's totally true, but here's the difference. The OH that we were dealing with bases was OH minus, was hydroxide ion. The OH in an alcohol is not an ion, it's covalently bonded. So it doesn't have a -1 charge. It's just sharing electrons with some carbon. So like the carbon would be like over here that it's attached to. So it has an OH covalently bonded to it. Again, the 8 strong bases are not alcohols. They are strong bases because when you add them to water, the OH minus breaks apart and separates and floats around on its own. Alcohols, when you put them in water, they are non-electrolytes. They stay together as an entire molecule. The OH does not separate. Okay, so alcohols have an OH in them. An OH just coming off of a carbon. Nothing else going on around it. All of these pictures here are just some different examples. Again, don't worry about the fact that its suffix is OL. Like, you don't care about that right now because we're not naming them. So alcohols are actually more acidic than alkanes, alkenes, and alkynes, which again is backwards if you're thinking of it like an OH minus, which is just one more example of why alcohols and hydroxides are not the same thing. So a molecule with an OH somewhere like there's this one has 3 of them. There's one. Like, so all of these are alcohols because somewhere in the molecule they have an OH. I don't care what else is going on in the molecule. Like over, so this molecule here has an alkene and an alcohol. So this is how these questions are going to work. Okay. So alcohols, I put them in their own category. They're just kind of alcohols. Okay. Aldehydes is the beginning of a category for me. Aldehydes are the very either first or last carbon. So the very beginning or the very end carbon on a carbon chain will have this. So the very end or the very beginning carbon. So there's my molecule. There's my very end carbon. The carbon is going to have a double bond to an oxygen. Now, when I draw it in skeletal format, I don't show this H right there because we don't show hydrogens. But if you super want to, I guess you can. That would be the aldehyde portion of the molecule. So again, really, it would just look like this. Okay, so it has to be first or last. That's the only, so it could be on this one, it could be on this one, but those are the only choices. And the way I remember this, and again, if this isn't helpful, that's fine. So, and this might just be me, but when my grandma used to tell me when I was little that I had to, behave or stop doing that or whatever, she was gonna spank my hide. She meant my butt. So aldehydes are on the butt, on the end of the molecule. So the aldehyde, the double bond to an oxygen, is at the end, like your butt. Yep, real classy. That's what's going on over here. Okay, so those are aldehydes. That's how you'd recognize an aldehyde. Ketones. Ketones are like an aldehyde, only not at the first or the last. It's a double bond to an oxygen somewhere in the middle. So in my molecule, somewhere not the first or the last carbon has a double bond to an oxygen. Okay, and the way I remember that is a key, like a key to unlock your door to your house or whatever. That's a beautiful key, I know. But your key has the long part that you put into the lock, but there's always a handle down here, and on the handle there's always some side on the left and some side on the right. So I think of the ketone as like there's the, I'm so good at drawing keys. The part that goes into the lock, and then the rest of the molecule is like the handle. So it can't be at the beginning or the end. It has to be in the middle. I can tell you that if, again, this is how I memorized it. Don't worry about how many years ago I did that. So I thought of it like a key, like a K-E-Y key. But I can tell you that Dr. Steuben hates that I tell people this because ketones are not spelled like this. That's bad. There's no Y. And because I use that example, sometimes people get that in their head, and I'm sorry, because she's going to be a real grouchopotamus about it. If you're taking organic chemistry with her, or really probably with any organic chemist, that you spell it correctly, which there's no Y in ketones. And that's what she says all the time. There's no Y in ketones. So ketones have that double bond to an oxygen on any carbon not the beginning or the end, not the first or the last. But they're similar to aldehydes, so I kind of group them together. And then the last one in this category are carboxylic acids. And they're kind of a combination of like aldehydes and alcohols, but not. So what happens is a carboxylic acid for the first or the last carbon. So at the beginning or the end of the carbon chain. So here's my molecule. Very last carbon. There's a double bond to an oxygen, which looks like an aldehyde, right? But that same carbon that has that double bond to an oxygen also has an OH. This whole thing represents a carboxylic acid. So if you run into something that looks like this, that is not an aldehyde and an alcohol. It's neither of those. That is a brand new, put together, completely different category, carboxylic acid. So a lot of the acids in our, like from the acid poster project are actually carboxylic acids. They're the kind of organic acids. A lot of the acids that wouldn't, with the weak acid, they're all, most of them anyway, are weak acids. But ones that you didn't necessarily learn how to name in Gen Chem 1 and yet all of a sudden show up in Gen Chem 2. So like lactic acid, formic acid, benzoic acid, acetic acid. Well, acetic acid you learned in Gen Chem 1. But all the other ones show up, they started showing up in Chapter 16, but you didn't know how to name them. They're just organic acids and they are carboxylic acids. So again, I know the OH looks like it's a base, but the reason why they're acids is that hydrogen right there. It's a very polar bond between that oxygen and that hydrogen. So that hydrogen is able to leave, is able to be donated, is able to go somewhere else. So carboxylic acids, the carbon at the end or beginning, however you want to look at it, of the carbon chain, that very end carbon has a double bond to an oxygen and an OH on that same carbon. And that whole thing, again, it's called a carboxylic acid. You wouldn't break it apart and call it an alcohol and an aldehyde. So I put those three together in a category because that just kind of, they fit together for me. Then another category I call it my old lady category. It's going to be the ethers and esters because I think ether and ester sound like names of old ladies. So an ether is in the middle of a carbon chain somewhere. A carbon is taken out and replaced with an oxygen. So in this, carbon, 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 not a carbon, that's an oxygen. Carbon, 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 carbon. You don't care what else is going on. There could be all kinds of business going on over here. What this molecule would have is that would be the ether part, and this would be the alcohol part. Like it would have multiple portions. But these don't have to be. It's in the middle of the carbon chain. There's an oxygen in place of a carbon. So oxygens are always going to have 2 bonds, just like how carbons always have 4 bonds, and I'll write this down at the end. So that's why on this oxygen, we don't have any hydrogens. There's just the 2 bonds to the from the carbon to the oxygen. And actually, that reminds me, we got to backtrack here. You know, when we do our skeletal bond line structures, we don't show our hydrogens, right? We don't show hydrogens coming off of carbon, but any other hydrogens have to be shown. So like, when you do the carboxylic acid, you do the double bond to an oxygen there, you can't just do an O right there. That oxygen is also bonded to a hydrogen. Whoa, I zoomed in. So you have to actually write the H there. You have to show H's when they're bonded to any element other than carbon. So if they're bonded to an oxygen or bonded to a nitrogen, those are the only 2 you're going to see. But you do have to show the H's in that case. So here, there's no H's, and I don't show an H because there aren't any. Oxygen only has 2 bonds. 1, 2. It's good to go. So an ether, somewhere in the carbon chain, there's an oxygen. An ester is like the fancy friend because it's like an ether. So somewhere in the carbon chain, there's an oxygen. And then in the carbon right next door, there's a double bond to an oxygen. That's the ester. The ester is right next to an ether. There's a double bond to an oxygen. So I put this in the category with ether instead of with the carboxylic acid and aldehyde and ketone stuff. Okay, esters have scents, so they kind of like the aromatic hydrocarbons. There are smells that come from this. So this is the last category. Last category are the nitrogen-containing compounds. So amines are the first one, and an amine is a compound that has a nitrogen anywhere, like it's just a nitrogen attached to something. Now nitrogens always have 3 bonds. I guess well, I'll write it here, nitrogen, 3 bonds. So when nitrogen is attached to the organic molecule, the carbon somewhere, it's going to have hydrogens attached to it as well, and you'll count how many hydrogens it should have, so that way it has a total of 3 bonds. Okay, so like for example, this one, carbon, carbon, bonded to nitrogen, okay? How many bonds does nitrogen have right now that we can see? Well, I just see 1, so it needs to have 3. So you could either write H, like to show the 2 H's, so now it has 3 bonds, which is how I like to write it. Or you could just do a condensed formula and write H2. Okay. This one, the nitrogen has, that's a 3. No hydrogens on it because it has 3 bonds already. So the for something to be an amine, it doesn't matter how many hydrogens it has. It just matters that there's a nitrogen in the molecule. Okay. These also have smells. They're just bad smells. Okay. And amines are also bases. We actually saw several amines in chapter 16 and chapter 17 when we were looking at weak acids and weak bases, and that this would have been our unknown in the weak base lab. That was the first lab that we weren't able to do this semester. So the last category, which I put in the same category as amines, is this. Now, when I look at the name, what do you think, like, how do you think you would say that? I would think amide is what I would think. They're supposedly correctly pronounced amide. And so if it were up to me, amide would not have an E at the end, but whatever. An amide or an amide is like a fancy amine. So wherever the nitrogen is in the molecule, in the carbon right next to it, the carbon that it's attached to has a double bond to an oxygen. So this has the same kind of relationship as ethers and esters. Amines and amides, or amines and amides, have that same kind of relationship. So I put those into their own category. So here's my categories. I put alcohols, which you will recognize an alcohol because there's an OH. I put alcohols in their own category. I just don't have a good place for them. And then I have aldehyde, which will have a double bond to an oxygen on the end carbon. Okay, I put that in the same category as ketones, which have a double bond to an oxygen in a middle, I did not clean my space well, middle carbon. Fine, I'm going to rewrite this and get it right nicer. Okay, so aldehyde, end carbon, double bond to an oxygen, like that. Ketone, middle carbon, double bond to an oxygen, and then carboxylic acid, no, why don't you work down here? That's beautiful. The end carbon has a double bond to an oxygen and an OH. I know that's funky looking, and I'm sorry. So next category are my old ladies. Ether, oxygen in the middle of a carbon chain. Ester, it's the fancy one. There's an oxygen in the carbon chain, and then the carbon that is attached to the oxygen in the chain has a double bond to an oxygen. And then my last category are my nitrogens. So amine, nitrogen anywhere. And then amide, it's the fancy one. next to the nitrogen, there is a double bond to an oxygen. Now that double bond to an oxygen is not coming from the nitrogen, it's coming from the carbon. Okay. So I broke this down into, I guess, 1, 2, 3, 4 categories, technically 5, because alkenes and alkynes are also on this list. I just am kind of assuming that you already know those. So here's what I want to just make sure we're all aware of. Carbon, as far as you're concerned, always has 4 bonds. Those bonds could be to any element, I don't care, but it always has 4 bonds. If a carbon does not have 4 bonds that we can see, it is assumed that there are hydrogens bonding to it that we just don't see. Oxygen, as far as we're concerned, always has 2 bonds. If we only see one visible bond to an oxygen, you need to add a hydrogen, and that hydrogen has to be shown. Show any hydrogens. And the nitrogens always have 3 bonds. And again, we have to show any hydrogens. You're not going to be doing much drawing of these functional groups. You're going to be looking at a molecule and identifying them. If you look at the beautiful worksheets that I have posted, there's plenty of examples of that. But when you're going to see this is when you work on the very last lab, the lab that is the molecular modeling one. You have to draw some compounds, and you need to make sure you follow these rules. Now, the first one, the carbon one, you need to know anyway. These rules came from the idea of formal charges in Gen Chem 1, drawing Lewis structures. These are the most stable arrangements of these atoms when they form bonds. Okay, so take a look at the worksheets for chapter 24 and definitely let me know if you have questions. Normally with this chapter, there's a whole lot of discussion and conversation and people are asking lots of questions, and I'm super missing that right now because that's when I learn what parts we need to talk about more, and I don't know. So just tell me if there's something I need to do more examples of, just please let me know. But do take a look at the worksheets and give them a shot. So that's how you'll know what you do and don't, I guess, know about this. So happy last lecture video of the semester.